I'm going to carry on talking about resistors, but talk about total resistance when you combine resistors in series and parallel. So when we connect resistors in series, you simply connect them in a chain. So this would be if you like daisy chaining them. This would be R1, this would be R2, this would be R3. When I connect resistors in parallel, you connect them in across each other, if you like, or in a loop. Now we have to find an expression for the total resistance of these three resistors and the total resistance of these two resistors. Now, the concept we have to use in this case is that the total potential difference between across here and here is the sum of the potential across resistance 1 plus the potential across resistance 2 plus the potential across resistance 3, V1, V2, V3. And that's due to the principle of conservation of energy. So conservation of energy says that V has to equal V1 plus V2 plus V3. We can't lose energy along the way. So if V equals V1 plus V2 plus V3, then, and since V equals IR from the definition of resistance, then the current times the total resistance, I'll call it V capital T, equals the current times R1 plus the current times R2 plus the current times R3. That is the potential across the first resistor plus the potential across the second resistor plus the potential across the third resistor. And because the current is the same flowing through all resistors, it can't go anywhere else, then we can actually cancel the current from each of these terms. It's a common factor. And we have the expression for the total resistance to be the sum of the three resistances. However, in this case, it's a bit different. The current here, energy is also conserved. We have to use, for the derivation of the formula, we have to use the fact that charge is conserved. So the charge going into this junction here is split into two components. Let's call it I1 and I2. And the I1 flows through R1, joins up here, and flows out here. And then I2 flows through R2, joins up at this junction, and flows out here. So due to the conservation of charge, or conservation of current, we have that I equals I1 plus I2. Now we know from V equals IR that I equals V over R. So V is the potential across the whole circuit. So the total potential across the combined resistance, or the total resistance, equals the potential across R1. Now it actually turns out that the potential across R1 and R2 are the same. They have the same energy per unit charge, or is that you have to do the same amount of work per unit charge to move a charge from here to here going via R1 as you would here going via R2. So V over RT is V over R1 plus V over R2. So in this case the common factor is V, the potential difference. And I could divide through by V, which leaves me with the expression 1 over the total resistance equals 1 over R1 plus 1 over R2.